that good? Okay, so let's get started. So I'll go to the next topic in the course, which is going to be on processes and threads and scheduling and virtualization. So today we'll start with what is a process, which I presume most of you already know, talk about threads, thread management and so on. And next time we'll start getting into more of the scheduling oriented aspects of the topic. Okay, so let me start with a review. So this is most of this next 2 or 3 slides is material from an undergrad operating systems class. So if you are if you've taken this class, you remember that material, bear with me, this should be all very familiar, but I just want everyone to be up to speed. So I'm just doing a recap from undergrad OS material. Okay, so these are all concepts you should be aware of or know. Multi-programming versus multi-processing. Multi-programming basically means that you are able to run more than one program concurrently on the machine. So essentially it allows you to run more than one process on the same machine. Okay. Multi-processing or multi-processors rather means that you have more than one processor or more than one CPU or core on the machine. Okay. So you can actually run things in parallel. It's not just concurrent, but 2 processes can run on 2 cores at the same time. So you get real parallelism as opposed to multi-programming where you're time sharing or switching between processes. Okay. So you get illusion of concurrency, but not real concurrency, because multi-programming can actually happen on a uniprocessor as well. Okay. Now the kernel data structure that the OS maintains to manage all of the processes is called the process control block. Okay, or the PCB. It keeps track of every process that is running, who owns that process, where the memory contents of the process are, what files are open, what the priority of the process is. All of that information is maintained in a data structure by the kernel, and that's called the process control block. Okay. Now each process is going to have an address space. The address space is essentially the set of memory addresses of that process. Okay. So depending on the size of the process, you are going to be able to address some parts of memory. Okay. Now typically the process address space essentially goes from 0 through n, where n is the size of the process in bytes. Okay. Although the process may be loaded at arbitrary regions of memory, and there is some address translation logic that is going to convert from logical addresses to physical addresses. Okay. So now every process over its life cycle is going to make a transition. So when you start up a new program or an application, it basically instantiates a process. Okay. The process starts in the new state where you start loading the code for that process, set up the memory and so on. And then from that point on, it's actually going to be able to execute. And the execution involves transition between 3 states. Okay. There's a run state where it's actually running on the CPU. Okay. It's scheduled to run. Okay, it could be in the wait state where it's waiting for I/O, waiting for some event, waiting for a lock or whatever other resource it needs. Okay, so when it's in wait state, it cannot run because it's waiting for something to happen. Okay, or it could be in ready state, which means that it's not waiting for anything. It is ready to execute, but is actually waiting for its turn on the CPU. So you are going to cycle between ready, run, and I/O or wait. Okay, so you're going to cycle between these states for many, many times, and then eventually your execution is going to complete, and then you'll go into the finished state. So essentially, that's your life cycle of the process. You start the process, then once it actually starts running, you will cycle between waiting, running, and waiting for the CPU, okay, or being ready for execution, and then you go into the final finished state. Okay, those are the state transition diagrams or state transitions of a process, and there's a diagram that basically allows you to cycle between these processes. Okay. Now with that concept, let's start talking a little bit about uniprocessor scheduling, because that will set the stage for multiprocessor scheduling and distributed scheduling, which we will talk about really in the next class. Okay. So there are many scheduling algorithms that the kernel can use to decide what process to pick next. Okay, the goal of your CPU scheduling algorithm is to decide of all the processes that are ready, which means they are actually waiting for their turn on the CPU, which one gets to go next, which one is going to execute next. Okay? And you can use many different policies as is shown here. Round robin simply says you're cycling between them in round robin order. Okay, they are sitting in a queue, take the first one, okay, because these are what are called preemptible scheduling policies. When you pick up process, you give it a certain amount of time on the CPU, which is called the quantum. Okay, the quantum is the duration for time for which it is scheduled. If the process runs and uses up its quantum, even if it has more work to do on the processor, it has to give up the processor. Its time slot is over. Okay, it goes back to the end of the queue. Okay, so you are going to cycle one time slot at a time. Of course, if in the midst of your quantum you start doing I/O, then you immediately give up the CPU because you are going to go into the wait state. You can no longer run. You have to wait for that I/O to finish to continue execution. So you may not use your entire quantum if in the midst of the quantum you have an event or you want to do I/O. But if you're a CPU bound job, you use up your entire quantum, then your time slot is over. You essentially go back to the end of the queue in a round robin policy. Okay? The shortest job first policy, which says that take all the processes that you have in your ready queue, pick the shortest one and run it first. Okay? So this policy can give you optimal waiting times, which means that the amount of time you wait in the ready queue is the least of all policies that you can ever design. Okay? So that policy has a good property, which is it optimizes wait times. Okay? Now the not so good part of the policy is it's not practical because it requires that the CPU scheduler or the operating system have knowledge of the length of the job, length of the process, okay, of execution time of the job. Which when you start a process, let's say you start a browser, how is the OS to know how long you are going to run it? How much CPU time it will need? It doesn't know because that's up to the user and it may change every time you start up the browser. So typically you will not have exact knowledge of job length. So as a result, you cannot pick the shortest job if you don't have that knowledge. Okay, if you knew those statistics somehow, then this is a good policy because it optimizes wait time. But in practice, in the general system, you would not know that. Okay. FIFO is just first come first serve. It just says that let's run them one at a time. Okay, lottery scheduling is a randomized algorithm. These other ones are not. So lottery scheduling, what happens is every job that is ready to run gets a certain number of lottery tickets. Okay, and then you take all the lottery tickets of the ready jobs and you run a lottery, meaning that you pick a winning ticket. Okay, and the job that holds the winning ticket essentially executes next. It's completely randomized because it's a randomized draw. You pick one ticket out of n that all the processes own collectively, and the one that owns the winning ticket essentially gets to go next. Okay. Now the interesting part about this algorithm is it is randomized, but also by controlling the number of lottery tickets you allocate to each process, you can control the percentage of CPU time it is going to get. Okay. So let's say there are two jobs, each of them gets one lottery ticket each. Okay, the probability of winning the lottery is half. Okay, so over a long period of time, because it's randomized, you will see that each job gets half the CPU time. Okay, but now if you give one job two lottery tickets and the other job one lottery ticket, the first job has twice as much chance of winning the lottery. Okay, because 2/3 is the probability of winning the lottery, the other one is a third. So that's going to get, so it's going to win on average 2 out of 3 lotteries. So it's going to get 66% of the CPU time and so on and so forth. Okay, so the nice thing here is by controlling the number of lottery tickets you send and how much each job gets can be decided by the user. Okay, you can also control the amount of CPU time that job gets on average. Is that clear? Okay. There are other algorithms. The EDF stands for earliest deadline first. Okay, this is a real-time scheduling algorithm. There are many jobs that may have real-time constraints where certain subtasks within that job need to be completed by a certain deadline. Okay, let's say you are doing speech processing or you are doing video streaming and whatnot. There are timeliness constraints associated with it. Right? So if for example, when you are decoding a video, if you cannot finish that decoding in a time, then your video will freeze. Okay? That's not pleasing to the user, but so that also says that certain tasks will have deadlines and you need to finish them by deadline. And earliest deadline first is a policy that essentially schedules these jobs that have real time considerations. Okay, and you essentially, as the name suggests, if you have some number of ready jobs, you look at the deadlines and you pick the one with the earliest deadline. Okay, the most urgent task goes next. Okay. So, those are a set of policies which are all uniprocessor scheduling policies. Any questions on this so far? Okay, now there are many performance metrics that you may want to strive to achieve when you decide what scheduling algorithm to pick. So, you might say I want to maximize throughput of jobs, okay, the amount of work that they complete per unit time. Okay. You want to maximize the CPU utilization. You want to use as much of the CPU as possible for a certain number of jobs. You want to maximize turnaround time, which is the completion rate of jobs, the rate at which they finish. Okay. Or you want to minimize response time. Okay. You want to make the system highly interactive. Or you want to maximize fairness, which means that jobs should be treated equally, not differently. Okay. So, these are all metrics. Okay, you might have to pick some subset of these metrics. Now, one thing that you should keep in mind is that no scheduling policy can optimize all of them together. Okay. When you try to optimize one metric, it is often at the expense of something else. Okay. If you make one metric better, you are going to lose out on something else because it is not possible to actually optimize all of them simultaneously. So, you have to decide what kind of system you have and figure out what metric makes sense for the system and optimize it accordingly. So, for interactive systems where it's, let's say, a desktop or a phone where users are interacting with that device, you want to minimize response time. You want the system to be interactive. You don't want it to feel sluggish. Okay, so, you want to pick a CPU scheduling policy that is going to minimize response times for you. Okay. But if you have, let's say, a large cluster, okay, such as Swarm or Gypsum that you may have heard of, where you submit jobs and it computes so for each of those jobs, you might want to maximize throughput or the turnaround time, which is the rate at which the jobs finish. Okay, interactivity is not important there because these are all bad jobs in this case. Okay. So, different systems might have different performance metrics that make sense for them. Okay. So, you got to decide what those are and then pick the right policy from an operating system standpoint. Okay. Now, I will not spend too much time on this slide other than to say that if you look at any process that is executing, you will see that over its lifetime, it is going to spend some part of its time computing, doing computations on the CPU. Okay. And some part of its life cycle is going to spend doing I/O, where it is reading or writing files from disk or reading or writing over a network. Okay. So, most processes alternate between processing and I/O, okay, computation and I/O. Okay. Now, depending on what fraction of the time they spend doing computation and what fraction of their time they spend doing I/O, you get different types of jobs. Okay. Jobs that primarily do computation are called CPU bound jobs. They spend most of their lifetime doing computation, very little time doing I/O. Okay. Jobs that spend most of their lifetime doing I/O are called I/O bound jobs. Okay. And then there are jobs in between that might do a mix of the two, or over their life cycle they might become CPU bound, then they start writing out some results they have computed, they become I/O bound and they do more computation. So, they might even alternate between computation and being computation bound and I/O bound. Okay. So, those are the behavior of job. Now, what this graph and this set of equation shows is, if you actually look at the amount of time jobs do computation before they do their next I/O and plot the distribution of what are called CPU bursts. Okay, the time spent between any two I/Os is called a CPU burst. Okay. So, if we look at the length of CPU burst, it basically essentially follows an hyper exponential behavior. All that means is essentially as shown in that figure, it means that most CPU bursts are small, right, which means the time spent on the CPU between any two I/Os will be small most of the time, but there will be some bursts that are very long. Okay, so, which is essentially why there is a long tail to this distribution. Okay, this basically the bump here says that there are lots of CPU bursts are small, short in size, but there will be some CPU bursts which are very long. Okay, so there is essentially that kind of behavior that's empirically determined based on observing many different types of jobs. Okay. And we will use this observation in the next slide where we try to think of a better CPU scheduling policy. Okay, so keep in mind that there are lots of short jobs, or not jobs, but short CPU bursts, but there are some that are long. Okay. I won't go into the equations of what hyper-exponential distribution looks like. That is what the equation is, but we don't need to worry about that here. Okay. So now let's think about how you use this information to design a CPU policy that can actually do somewhat better than some very simple ones we talked about already, which is round robin and others. Okay. So this one, okay, is essentially called a multi-level feedback queue, and it uses several different things. First, it uses a policy which is called priority queues. Okay. Priority queues essentially says that the scheduler has more than one queue, and each queue has a priority level associated with it. And there's a tiny picture here which you probably can, hopefully can see from the back. You see 3 queues here. Okay, so these are priority queues. That's the highest priority, and the lowest one is the lowest priority. Okay, depending on your priority level, you will join an appropriate queue. Okay. And the CPU scheduler just does priority scheduling, which means it looks at the topmost non-empty highest priority queue and picks a job from that queue. Okay. So you start at the top, says is there any job at the highest priority level? If so, you schedule it for a time slice. Okay, if that queue is empty, you said you look at the next highest priority queue and is there a job there? If so, you schedule it. So always you will pick the highest priority job from among the priority queues and schedule it. Okay. That is what is called priority scheduling. Okay, now jobs have different priorities. So depending on the priority, you will prefer some over the others. Okay. Now multi-level feedback queue essentially builds on this notion of priority scheduling, and it does the following. Okay. When a new job joins the system, you will not know what its priority level is, so you will just put it in the highest priority queue. Okay. Whenever a new process starts, you say I will actually put it at the top queue. Okay. Now the scheduler is always going to do the following. It's going to be doing priority scheduling. So it's going to pick the highest priority job. Okay. And you run it for a time slice. If that job uses its entire time slice, okay, you label a CPU bound and you drop it one priority level. Okay. Or if the job, so there are only one of two things that will happen when you give a time slice to a job. Either it will use its entire time slice or it won't, meaning it will do I/O in the midst of its time slice. If it uses its entire time slice, you call it CPU bound and you drop its priority. If it does the opposite, which means if it starts doing I/O in the midst of its time slice, you increase its priority by 1. That's our rule. Is that clear what I said? Okay, we'll ask why this makes sense, but first it should be clear what we are saying. Every time you pick the highest priority job that is in the system, you give it a time slice and you observe its behavior over that time slice. If it uses its entire time slice, you drop it one level. Okay. If it does I/O in the midst and it does not use its time slice, as a result, you increase its priority level. Okay. That's our rule of how we are going to schedule. Yes, question. Time slice essentially means you get a certain amount of time to run on the CPU, yes. You schedule it for that amount of time. Yes. Any questions about what I just said? Okay, so now let's ask the following question. What does this do? Okay, why did we actually make this rule? Okay, or let me ask a slightly more specific question. What does this do to let's say I/O bound jobs versus CPU bound jobs? Yes.
So I/O bound jobs get immediate real-time feedback because they got higher priority, but they don't use much computation, so they give it back sooner than the CPU bound task that use the entire time. You still get to use the entire time, but you still have I/O getting back.
Okay. Right. So somebody else wants to add to that, and we'll talk. I'll just describe what you said, paraphrase it, but yes, go ahead.
It will cause a process starvation. Like some process will
Okay, so we will come to starvation in a moment. I'm simply asking what does this do to IO bound and CPU bound jobs, right? Anybody else have anything to say? So first let's ask what does this do to IO bound jobs in terms of priorities. Okay, so it should increase its priority because we said IO bound jobs are the ones by definition that do a lot of IO. So it's highly probable that in the midst of its time slice you might actually do an IO, trigger an IO instruction. So as a result, you will rise in priority. That's our rule. Okay? So all IO bound jobs by definition, as soon as they start doing IO, they start rising in priority. Okay, and what about CPU bound jobs? Yeah, they have to drop because that's the same rule applies. CPU bound jobs are ones that rarely do IO. So if you give them a time slice, they might use the whole time slice with high probability. That will cause them to drop. Okay? So in this 3 queues, most of the IO bound jobs will end up at the top and most of the CPU bound jobs will end up at the bottom. Okay? Yes, question.
How is this different from the shortest job?
Okay, that's a good question. So question is how is this different from the shortest job first? Okay. So now as we just said, the IO bound jobs are at the top, CPU bound jobs are at the bottom. Okay. Okay, and now what does this tell us? This tells us that we are favoring IO bound jobs over CPU bound jobs because the highest priority queue will favor those IO bound jobs by definition. Okay. That's number one. So we have given higher priority to IO bound jobs over CPU bound jobs. Second is IO bound jobs are the ones that are actually shorter because they use a fraction of their time slice, and CPU bound jobs are the ones that are longer because they are actually using all of their time slice and they want to compute more. Okay? So this is now beginning to approximate shortest job first without actually needing any knowledge of the job length. Remember that shortest job first actually required that you needed to know the job length. Okay? In this case, just by observing what the job does and having no extra knowledge, we are beginning to approximate what SJF does. Okay, and we said SJF has a good property, which is it minimizes wait times. Okay, so this policy is also going to give you that property without having to require that knowledge of job length. Yes, question in the back.
Are the jobs basically just like sequences of a program that all have the same ID, like represented by the rectangle there, or is each job one rectangle?
Okay, the question is what is a job? So forget the rectangles and circle. A job is a process that is executing. Okay, so essentially that queue is just showing you all the processes that are sitting in that queue waiting for a turn to run on the CPU. Okay, so the top queue here, which has what you said, 2 rectangles, essentially says there are 2 jobs or 2 processes, process 1 and process 2 that just need to execute. This job, this queue has 1 job and this queue has 2 jobs. So there are 5 processes that are executing in the system. Process and jobs are being used synonymously here. Okay.
So when you say that the job goes up priority or down priority, does that mean the job ceases to execute and has to restart after being moved, or is a portion of the job executed and then the rest of it moved up or down?
Okay, so the question is when the job is actually changing its priority level, is it actually going to just take a partially executed process and continue execution at a lower priority, or are you restarting that job? That's your question. So in this case, this is CPU scheduling. So you're executing jobs or processes as they go along. So all of these are currently executing processes, which means they have partially executed some part of that process or program, and there's some more execution to go. Okay? So you don't restart the job, you're simply changing its priority level, and as and when it gets to run on the CPU, it executes some more. Okay? That's how all of these jobs will execute. Any other questions? Yes.
Can you generalize it by saying that most processes are initially IO bound and then maybe like they might use the CPU later? So does it happen that you initially give higher priority to all the processes and then?
Right. So question is, can you say that all processes are IO bound and then they become CPU bound? So I don't think we can say that processes are IO bound initially. What we did say, however, is when a job arrives, you don't know what it looks like. So you just give it the benefit of the doubt and start it at the highest priority level. If it just happens to be a CPU bound jobs, in 3 time steps it will drop to the bottom because every time it will drop. Okay, if it is an IO bound, it will stay there. So then you very quickly discover what kind of job it is. Okay. Any other questions? Okay, yes.
Because we are doing it because that every process gets almost equal share of the CPU time. Isn't the reason for doing it?
The question is that why are we doing this at all? The reason we are doing this is we want to ensure that the IO bound jobs, which are the short jobs, okay, they execute quickly and go back to doing IO, and then you can use the CPU to run the CPU bound jobs, which are the longer jobs. Okay, so it's not that they're getting equal time, they're actually getting unequal time, because the IO bound jobs take very little CPU time at all. They spend most of their time doing IO. So if they become ready to run, you run them at high priority, and then they go back to doing some file IO or some such thing. Okay, yes.
Is there any benefits if you increase the number of priority queues?
Okay, is there any benefit if you increase the number of priority queues? That depends on what you're trying to achieve in the system. Typically, most real systems might have as many as 16. Okay, I've only shown 3 here. That gives you fine-grained ability to distinguish between type of jobs. Okay, but you can do the same thing with 3. The broad property will stay, but you will not get as much fine-grained distinction between types of jobs. Okay, yes.
What does round robin in these level?
Okay, so I haven't finished. So the last thing I want to say is, after distinguish between IO bound and CPU bound jobs, the last thing I want to mention is this is a priority queue. So if there are multiple jobs that are, or processes sitting in a priority queue, you are going to do round robin. Okay? So let's say the top queue has 2 jobs. You are basically going to run the first job, okay, and then you are going to run the second job, and essentially is going to round robin. So you are doing round robin within each queue, and if that queue becomes empty, you go to the next non-empty queue in priority order and run jobs in round robin order. Okay? Except that it's unlikely that a job rejoins the same queue, depending on its behavior is going to rise or fall. So you will essentially end up doing round robin only at the bottommost queue, where the job will rejoin. There's no more priority levels to drop. Okay, but that's the policy. Okay, so this is called multi-level feedback queue. It's common scheduling policy used in many operating system kernels. Okay, but what it should tell you is we are approximating shortest job first without having the disadvantage of requiring to know job lengths. Okay. Okay. So we are done with the process overview. We are going to switch gears, talk about threads. Quick announcements before I move on. The TA posted office hours. I just wanted to say that here. TA office hours are going to be Tuesday, Thursday, noon in the LGRT, which is the tower that's attached to, actually I'm pointing the wrong direction. It's in the other direction there. Okay, so if you need to meet with any of us, I have office hours Monday, Wednesday. TAs have office hours Tuesday, Thursday. We'll have one more office hours announced soon on Friday. At the moment, that's not yet been scheduled. Okay, so 4 out of the 5 days, you can see one of us. Okay, so let's move on. So next module is on threads. Okay, so this is not as much of a recap, but if you know threads, you're probably also familiar with some of this. Okay, so let's now take the notion of a process and generalize it to what we call a multi-threaded process. Okay, so let's understand what a process is first. Okay, if you take any process that's executing, it's going to be have some code and data resident in memory. Every process is going to have some code that you loaded in memory, and it has some data. The data could be on the heap, it could be on the stack. Those are all variables that are data structures that that process maintains in memory. Okay? And then the process is actually executing its code. Okay? There's basically going to be a program counter that the CPU has. The program counter points to the next instruction. You get that instruction, you execute, and you continue execution. Okay? So essentially, a traditional process has a single thread of execution that is going through that process, and that is what is actually executing next to that process. Okay? That is what we mean by a traditional process. Okay? Now, when we call what is a thread, essentially a thread is going to generalize this notion, and we are going to allow multiple streams of execution to share that same code within that process. Okay? And I'm going to draw a picture to just show you, if I can find. So let's say that's a process. Okay, that's resident in memory. That's address 0. That's address n. Okay, let's call this the stack, there is the heap. Okay, stack grows downwards, heap grows here. That's the code segment. Okay, so let's say there's the main function, there is some instruction here, there's function foo, there's some instructions here, a code here, and so on. Okay, if you had a single threaded process, you would start at main, you will execute the first instruction, second instruction, maybe you call foo in here, then you jump there, you execute this function, come back here, etc., etc. Okay, so you have essentially one stream of execution. There's one instruction being executed at any given time. Okay. If you have a thread, you are going to allow multiple streams of execution. While this thread, which we will call T1, is executing that instruction, another thread can actually execute some other part of that process concurrently. Okay. Each of them is executing sequentially, but they are independent executions. Okay. So in this case, thread T1 is executing some code in main, thread T2 is at the same time executing some code in foo, and there may be many other functions and many other threads that are concurrently executing other parts of that process. Each thread of execution is going to execute sequentially. You will go to foo, you will execute the first instruction, second instruction, you might call some other function, and so on and so forth. Okay. So now you have concurrency within your address space. Okay, multiple instructions are getting executed concurrently by multiple threads of execution. Okay, so your process has essentially become concurrent and has multiple threads of execution. Okay, that is what we mean by a thread. So it's a flow of control or execution through an address space. An address space now can have any number of such threads that are all executing different parts of the code at the same time concurrently. Okay, is that clear? What I just said. All right. So what does this have? So essentially now each thread, okay, is going to share the stack and the heap, but each thread gets its own set of registers. Okay. So essentially this thread is going to get a program counter that is pointing to the next instruction to execute. This thread has its own program counter that's essentially pointing to the next instruction it has to execute, and so on. It will get its own set of registers and so on. So threads essentially have their own, they share the heap, but not necessarily the stack, and they essentially get their own program counters, okay, which tells them what they need to execute. I have a picture here, I think, yes. So you will see in this picture, so each of these boxes is essentially a thread. It has a program counter, it has a register, and you see each of them as a stack, so that they have their own local variables stored in that stack. But the rest of the code is shared, the heap is shared, and so on. Okay. So now you have made your program concurrent. Okay. If you actually have multiple cores on your machine, each thread can execute on one core, and now you get true parallelism. Okay, you are essentially processes executing in parallel on multiple cores. Okay, even if you are uniprocessor, you still get concurrency, but not parallelism. Okay, is that clear? Any questions? Yes.
Previous slide was when thread is a lightweight process. What does the meaning of lightweight there?
Okay, I'll come to lightweight processes. I'll talk about them just a little bit. Okay. Any other questions? Yes.
So you mentioned that multiple threads can run on different cores parallelly, and you get true parallelism. Is there a reason why multiple processes can't use the cores individually?
Okay, so the question is threads. I said that threads can run on multiple cores, you get true parallelism. The question is, can you not actually execute processes on cores? So indeed, if you have processes, they can also execute on multiple cores. Okay, so in that case, you are getting parallelism at a process level. Okay, two processes can run on two independent cores, and so now they are running in parallel. That will always happen. Now, if you want parts of the same process to run in parallel, then you have to have thread, because by definition, a process has only one thread, so it can only execute on one core. When you have multiple threads, you can actually run different parts of it on different cores. Okay? Any other questions? Okay, so now we can ask the question, what does this give us? Why do we want to use threads and so on? So first thing is the reason threads have become important is most common machines now have multiple cores. This was not the case maybe 10 years ago. Most of the machines you bought were uniprocessors. Okay, had only one CPU and one core. Okay. Now even your phones have 4 cores. Okay. These watches that you get are actually dual core, even though have multiple processors. So then you can ask, what do you do with all of these processors? You can actually use them to execute a single application in parallel. Okay, basically split it up into threads, and threads now execute different parts of that process in parallel. Okay. This allows you to get parallel execution of the process, and hence you might get better performance and so on and so forth. Okay. So as more and more systems essentially have multiple processors and multiple cores per processors, if you want to use these cores and processors rather efficiently, you have to use threads. Otherwise, you will need lots of processes that are always ready to run in parallel. That's the only way you will use all of the cores that you have on the machine. Okay. Yes, question in the back.
A uniprocessor system, if I have threads that are IO intensive, so can we run like multiple threads so that the CPU usage is like low, but because they are IO intensive, we can get a benefit?
Yes. The question is, even in a uniprocessor system, can you use threads in some effective manner? That was basically, I'm paraphrasing your question, right? So the answer is indeed yes, because what happens is if you have multiple threads in a single process, and let's say there's only one core on your machine, okay, you run thread 1. Okay. If thread 1 starts doing IO, that thread is going to block, it's going to go on the wait state. Okay. If this was a single threaded process, the entire process is going to block. None of it can continue execution, because that's what we said. Now, if it's a multi-threaded process, while that thread is actually doing IO, you can still run other threads of that process. So the process as a whole can continue to make progress even if some threads of that process are blocked doing IO. Okay. So this is how you can take benefits of threads even on a uniprocessor. Even though you don't get true parallelism, the process as a whole can actually continue some progress or have some execution if some threads are blocked. But if you had a uniprocessor system and a single threaded or a traditional process, as soon as that process does IO, the whole process blocks. Okay. Any other questions here? Okay. So first point is that there are multi-core systems, multi-processor systems. Threads allow you to take advantage of them. The second point that I want to make is switching between threads is more efficient than switching between independent processes. Okay. Whenever you do the CPU scheduling decisions, I said that you switch from one process to another as soon as the time slice ends. Okay. There is some bookkeeping that the CPU has to do in order to switch. Okay. It has to save the state of that process, load the state of the next process that it wants to run into the processors, and so on. So these bookkeeping operations are called context switches overheads. Okay. So context switching is more expensive when you're switching between processes. When you're switching between threads, it's the same process that's continuing to execute, you're just switching between threads. So it's a much more lightweight context switch. Okay. So context switches are much cheaper and more efficient when you're switching between threads of the same process as opposed to two different processes. Okay. So that is one thing that too you want to keep in mind. And then the same thing is true as far as thread operations are concerned. Not only are context switches cheaper, creating a thread is cheaper than creating an entire process, deleting a thread is cheaper than deleting an entire process, and so on, because you don't have to set up the entire process, load it in memory. It's already loaded. You're just creating another thread within that process. If you had to create a new process, you would have to load that entire program in memory first. Okay, so much more expensive. Okay. So thread management is cheaper than process management. Okay. Threads can actually share the same address space. Okay. And we'll see that allows us to do several interesting things like pass data around without having to send explicit messages and whatnot. Okay. That we'll come to. Okay. And last but not least, threads can actually execute in parallel on multiprocessors or multiple cores. Okay. So you can get true parallelism for processes, which you wouldn't get if you had a traditional process. Okay. So now there's a few more things I want to say, then I will actually move on to other aspects of threads. So what is shown here are essentially the gradation or the progression from a traditional process to a multi-threaded process. Okay. So in a single traditional process is also a single threaded process. Okay. If you have a process that has only one thread, that's the same as what we've been calling a process. Okay. So in this case, the way you typically write this code is you might make blocking IO operations or blocking system calls, and whenever you do any IO or make blocking system calls, the entire process is going to block. Okay? And furthermore, a single threaded process by definition cannot have any concurrency or parallelism, because there's only one thread, there's nothing you can do in parallel. Okay? So that's one end of the spectrum. Okay? And then at the other end of the spectrum, you have multi-threaded process, okay, where is a process with multiple threads. In this case, threads also make blocking calls. So the way you write the code is exactly the way you are going to write code for a single threaded process. You can read files, write files, or make any of these IO operations, and that is going to result in blocking calls. But when you make these blocking calls, only that thread will typically block. Okay? It depends on the threading library, as we'll see, but if done right, only that thread blocks, other parts of the process can continue execution. Okay? So you still get parallelism as a result, and if you have multiple cores, you are going to get true parallelism. Okay? So threads are going to retain the idea of a sequentially executing process, but generalize that. Okay? It allows you to make blocking system calls and yet get concurrency or parallelism. Okay? So that is the advantage. And from a software engineering perspective, okay, it is much easier to write applications this way, okay, where you take a large process, you split it up into threads, and then allocate certain tasks to each thread. And I'll show you some examples of how you can do this. And then each thread does its own task, and the threads communicate with one another, and so on and so forth. Okay? So that's something you want to keep in mind. And I think I have an example or two here. Okay, so there are two examples. I'll talk about a browser and a web server, but there's a question there. Yes.
In the event that you have more threads than cores available, do you follow similar scheduling policies as you do with processes, or is there a different or better way to handle that?
Okay, the question is, if you have more threads than you have cores or processors, is there a way you want to schedule these threads that is different from what we talked about? Okay, so everything I said about scheduling policies applies equally to threads or processes. This is why I was using the term jobs or tasks, because that's in the job or a task could be actually a thread within a process, or it could be a traditional process. Everything applies equally well. Okay, so if you have a system where there are threads within processes, then essentially each thread gets scheduled independently, typically. And I will talk about that in just a moment when we get to types of thread management packages and so on. Okay? So the same policy applies. From OS perspective, no different, because you want to now run a thread as opposed to running a traditional process. Okay? So it's the same kind of thing. Any other questions here? Okay. So let's talk a little bit about how will you take some applications you know about, let's say a browser, okay, and then partition it into threads. Okay. Now let's first try to understand how would a browser work if you had a traditional process implementing a browser. So let's say your browser process, user has clicked on a link within an HTML page. Okay. So what needs to happen? So when you click a link, you need to first connect to the server that URL points to. Okay. You set up a network connection. Then you actually send the request, which is maybe you want index.html or whatever page that URL points to, or that network connection. Okay. Then you wait. Okay. You wait for the HTML page to come. Okay. Then you are going to parse that HTML page. Okay. Look at what is in it. If there are embedded images in that page, okay, you got to make one connection for every image and download that image. Okay. Once you have downloaded all parts of that page, okay, then you basically have to then render all of that text and image into a layout, and then essentially display it on the screen. Okay. That's how typically a browser is going to work. Okay. That roughly matches with your notion of what happens when you click on a link. Right? Now, if you do this in a traditional process, each of these steps is going to happen sequentially. Okay. So user has clicked a link, and you got to wait for the HTML page to be downloaded, all the images to be downloaded before you can actually see any part of the page, because the rendering of that page is the last step within that process. Okay. So the latency that the user is going to see is the sum of the latency to download everything that the page contains, including ads and whatever else might be in it. Okay. So that's the latency that the user is going to see. Okay. Now let us assume that you make this browser a multi-threaded process. Okay. There are many threads. Each of them can execute concurrently or in parallel because there may be more than one core. Okay. So initial steps have to be sequential. You click on a link, you are going to set up a network connection. Okay. You are going to get the HTML page. Okay. Then maybe a different thread that is going to parse that page. Okay. Is going to find that there are 10 images in there. Okay. Now you no longer have to download those images sequentially. You can start 10 threads and they can make 10 connections and get them in parallel. Okay. And while those images are downloading, your rendering thread can already take that HTML page and start displaying some parts of the text while the images are still loading in the text. So the user starts seeing responses even before all of the page has even been downloaded from the server. Okay. Because you are now getting benefit of parallelism. You can give better interactivity. You don't have to wait until everything has been done. Okay. And that's how most of the browsers behave. If you actually see when you click on a link, you might see the text appear first and the images are still loading sometimes. Okay. Because you actually have threads that are still fetching them while the text has already been fetched and so on. Okay. So that's essentially how you can take a browser and make it multi-threaded, and hopefully with this very simple example you are now convinced that making it multi-threaded is actually giving you better performance, lower latency. Okay. Same is true of the server. Okay. This is now why do you want to make a web server multi-threaded. Okay. Let us first take a single threaded server. Okay. What does a server do? It waits and listens for requests. Okay. User sends an HTTP, user in this case is a browser sends an HTTP request to get a page. Okay. The server is going to wait for the request, is going to get that request, process it, send back the whatever has been requested, whether it's a HTML file or image or whatever it is. Okay. It's going to get the next request and so on. Okay. So most servers are essentially a while loop that are just sitting there waiting for the next request, process the request, wait for the next request and so on. Okay. Now, if you did this sequentially, while request 1 is being processed by the server, if a next request comes, it has to wait because you have only one thread, it's still processing, it's still busy working on the first request, so it cannot even start processing the next request. So your requests are just going to start queuing up here. Okay, and then your browser thread, not the browser, the server thread is going to take one request at a time, process it and send back responses. Okay. Now, if you make your server multi-threaded, that need not be the case anymore. What you will do is you will have multiple threads. Okay. Each thread is waiting for a request. First request comes, you assign it to one thread, and that thread goes off and starts processing that request. Okay. When the next request comes, there are still many other threads sitting there waiting for request. So give it to the next thread and so on. So that both of these threads can now process those requests in parallel, no longer in sequence. And as a result, the end user or the browser that's waiting for the response also get faster responses because the queuing delay has been reduced at the server. Okay. So that's the scenario shown here. Okay. So essentially this is called the master thread or a dispatcher thread that is essentially assigning work. It is the one that's waiting for requests, and whenever a request comes, it assigns it to one of the n worker threads that are the threads that are actually going to do the work. Okay. Now, depending on the number of worker threads, you are going to get a certain level of concurrency. There are n worker threads, you can process n requests concurrently. If n plus 1 requests all arrive at the same time, the last one has to wait because all the worker threads are busy. Okay. So the size of the worker pool is going to actually determine the amount of concurrency or even parallelism that your server can provide. Typical servers will have lots of worker threads, so you can work on many requests all at the same time. Okay, but depending on that size of that pool, you are going to limit how many you can process concurrently. And if more arrive than that, then you get queuing delays. Otherwise, there are no queuing delays. Okay. So that's a typical architecture of a multi-threaded server. Okay. Again, you see that it's better to do it this way than if you did it sequentially, because if in sequentially you will have long wait times for requests to get processed, because they are getting processed one at a time. Okay, is that clear? Okay, so we saw two examples. Now there are many examples like this. I won't go into others, but most applications that you actually typically run on your machine have become multi-threaded, like mail clients and whatever other application you can think of. They all have different threads doing different tasks in that process. Okay, we'll come back to actually thinking of browsers and servers later. This was just a high level example. And by the way, this is the same example that real servers like Apache web servers use. Okay. They do more sophisticated things than this. They actually can change the size of the worker pool on the fly depending on the load. If more requests start coming, they can start new worker threads on the fly and increase the size of the pool. But if the server is sitting there idle and there are lots of threads sitting doing nothing, you shrink the size of the worker pool. Okay, so they actually do more sophisticated management of how many worker threads to have and so on and so forth. Okay. Okay, so now let's talk a little bit about thread management, which will lead us to the last part of the lecture. So whenever you write your application as a programmer, you have to decide what threads to create, how many threads to create, what functions each thread is going to perform, and so on and so forth. Okay. Typically, you are going to use things like synchronization primitives, locks and semaphores or monitors in order for these threads to behave properly. Okay. If you have two threads and there is a shared variable, the access, you always have to protect that shared variable with a lock. Because if two threads try to access that shared variable at the same time, they might corrupt one another. Okay. That's a standard rule you have to assume. Whenever there's concurrency, you got to have some locks. Okay. All the shared variables have to be protected by a lock, because you don't want two threads to update the variable at the same time and trample each other, whatever they are trying to do with that variable or the data structure. Okay. So synchronization, okay, is part and parcel of all threading. And as an application programmer, you not only have to write threaded code, you also have to make sure the synchronization is right. If you don't protect shared variables with synchronization primitives, then your application is going to have race conditions and you might start seeing bugs. Okay. So it's very important to write this code well. Okay. So you might use things like condition variables and semaphores and locks and whatnot. Okay. It's generally assumed that you know at least what these concepts are from an undergrad course. Okay. If not, you should at least read up on that, because when you write your programming assignments, you will be expected to use these things, okay, in whatever language you choose to implement them. Okay. Now, so that's, I won't actually go into the synchronization primitives, but what I do want to talk about is how threads are actually implemented by the operating system. Okay. And by and large, you are going to see two types of thread packages, what are called user level packages and kernel level packages. And that is what we are going to talk about for the remaining 20 or so minutes, which is what is a user level thread, what's a kernel level thread, what's a lightweight process. Somebody had asked that question and I said I'm going to come back to that. And so we are going to talk about all of those things. Okay. And in doing so, we are going to ask all of these questions. Okay, for each of those types of implementing thread packages, what is the cost of thread management, what's the impact on scheduling, what's the impact on flexibility in terms of programming model, and what about things like blocking and so on. Okay, so let's start with user level threads packages. Okay. So first, what does it mean to be a user level threads package? Okay, essentially, in a user level threads package, the threads library, okay, is implemented completely in user space without any explicit support from the operating system. Okay. The operating system does not have explicit support for threads, and the whole abstraction of threads and the primitives to manage threads is completely implemented in a library in user space. Okay. An application can just use that library and use threads, the functionality that that library provides. Okay. That is what is meant by user level threads package. Okay. So in this case, the OS kernel is unaware of the presence of threads, because all thread management is being done in user space by the library that's part of the application. Okay. It is that library's job to actually create threads, delete threads, whatever the application chooses to do. Okay. So what are some advantages of this approach? The first advantage is you actually don't need any kernel modification to support threads at all. Okay. All thread management is actually being done in user space. No OS support is needed. Okay. The side advantage is if you have an old OS or an OS that was not designed to support threads, you can still write threaded code on that platform by using a user level threads library. Okay. Now, user level thread packages are quite efficient okay, because thread management are all library calls to a library that's part of that address space. They don't involve system calls. Okay. System calls are OS level calls where you call the OS and ask it to perform some operations. Okay. If your OS is not participating in thread management, doesn't even know about the presence of threads, all of that is being done in the library, then it should be clear that all the thread management calls that you make to that library are going to be very efficient. They're just function calls. Okay. So creating threads, deleting threads, all of that is actually very efficient because they don't involve system calls. Okay. Furthermore, this is going to be very flexible because different processes that are running on the same machine can use different thread level libraries. Each library is different. It could implement a different scheduling policy. You can have one that says I use round robin, another one that says I use lottery scheduling for the threads within that process, not globally. Okay. So depending on what your application needs, you can pick the library that provides such a function and use it. Okay. There's no restriction from the OS on what the scheduling policy for threads within that process is. Okay. So that gives you flexibility. So those are the advantages. Okay. What are some disadvantages? So the first disadvantage is because the OS does not actually know about the presence of threads, it views that entire process as a single threaded process. Even though there are actually threads in them, it doesn't see them. Okay. It only sees it as a single threaded process. Okay. So what that means is any one thread within that process makes a blocking call. It does any file IO, the whole process is going to block. Okay, because the OS doesn't know there are other threads in it that could potentially run. So it will block the whole process. Okay. So you no longer get some of the benefits that I had alluded to earlier, which said if one thread blocks, other threads can run, not with user level threads packages. Okay, because OS does not explicitly know. Okay, it cannot distinguish between a real single threaded process and a process that actually uses threads, user level threads. From its perspective, they look the same. Okay, that clear? Okay. The second disadvantage is you cannot get true parallelism either in this case. Okay. If you don't know as an OS that this process has multiple threads, how could you possibly schedule them on multiple cores? You don't even see them. Okay. So you can only schedule that process on one core. Okay. So the advantages of multiple cores cannot be exploited when you have user level threads package. You can only get process level parallelism in this case, not thread level parallelism. Is that clear? Okay. And the third thing is, of course, threads are going to compete with one another inside the process. The way scheduling would work here is the OS will schedule that process. Okay. Once the process runs, the threads library will run first and say which of the threads within that process should run. So it will run another scheduling policy inside that process and pick one thread to run. And those threads are going to compete and you can pick whatever policy, and then that thread is actually going to run for that time slice. Okay. So it's a two-level scheduling policy. Okay. One that's actually inside the OS that's picking a process, and there's one that's inside the library that's picking a thread within that process. Okay. Yes, question.
Sorry, this might be a very specific question, but how do you avoid blocking system calls?
How do you avoid blocking system calls? Okay. So if you want to avoid blocking system calls, you will have to actually use what are called non-blocking calls or asynchronous calls, which we haven't gone into yet. Okay. So there's a way to write user level threads and not how to block, but they requires that you actually use special calls that don't block. But traditionally, if you use any standard calls, you're going to just block. So then you are back to all of these problems. Yes, question.
Is there a way to create an interface where the kernel can know that these are threads and not a single process?
Okay. So question, is there a way for the kernel to know that there are some threads within that? I'm going to come back to that in 2-3 slides. Okay. Just hold off on that. Yes.
So web servers like Node.js, where they use event-based,
Yes.
they have access to these asynchronous system calls.
Yes. Okay. Is that your question? Okay. So question is, when you have systems like Node.js that use event-based programming, they have access to asynchronous calls. Okay. So I will go back 2 slides actually, because I did not mention that. I was going to come back to that. Okay, yeah. So So you see that between the single threaded process and the multi-threaded process, there's another bullet there which says finite state machine, which is event based. Okay, so that's the third programming model that sits between a single threaded and a multi-threaded process, where your single threaded process, but it uses something called event based programming, where you program based on events. Okay, each event uses non-blocking calls, so even if one event is done, you can switch to another event without blocking that process. Okay? So this increases the complexity of writing application because it uses a very different style of programming, okay, which is event based. It is all asynchronous. It requires you to jump based on into event handlers whenever an event is triggered and so on and so forth. We are going to come back to that at a later time because that is not going to use the threads abstraction, but there is that other way to program as well. Yes, question.
So now, nowadays there are something like async and await attitude languages, so you can write asynchronous program but in a synchronous style.
Yes. So there's the point that is being made is these days you can actually write asynchronous programs in a synchronous style. It is indeed possible to mix all of these models. You can have each thread doing asynchronous events, right? For example. So it's not just there are three, but there are hybrid models. So the model you are pointing to is a hybrid one. Again, we'll come back to that. Today's discussion is only about threads that use by and large blocking calls. No event based, no asynchronous calls as of now. Okay, we come back to that at a later point. Okay. So let's move on to kernel level. So before we move on, here's a picture of user level thread that I actually should have shown first. Okay, so here is essentially a process. Each of these blocks is a process. Okay, this is the OS scheduler. Okay, that's the processors. You have two cores or two processors there. Okay, as you see, each of this process is seen as a single block with one thread in it because this is a user level threads package. Okay, the OS only sees each of these processes as a traditional process, even though you see that inside that process there are multiple threads and there's a scheduler and so on. Okay. What this shows is these two processes have actually been mapped on to been chosen for execution. They're running on those two processors, and then when they run, the library scheduler has to pick one of those threads. Okay, so that is what has actually been shown there. The third process is not yet running. It's waiting for its time slice. Okay. Okay. So now let's talk about kernel level threads. Okay, kernel level thread is exact opposite. Everything I said about user level threads just flip. Okay. In this case, the kernel is aware of the presence of threads in a process. Okay. The kernel provides explicit support for threads within the process. It can see how many threads are within each process and schedule them explicitly. Okay. So you will see that again in the same example. Now if you implement those threads with the kernel level threads package, okay, you will see that each of these threads is now visible to the kernel. Okay? And the kernel is now directly scheduling a thread within a process, not just scheduling the process and letting the library figure out. Okay? You explicitly can see those threads and schedule those threads. Okay? So as a result, now you can actually get true parallelism because you can take, in this case, as you see, you take two threads from this process and you schedule them here. So now there are two threads from the same process executing on two cores at the same time. That's true parallelism for that process. Okay, so you can actually take advantage of some of these things, which means if you have multiple processors, you can actually get real concurrency or parallelism. Okay, so let's talk about advantages. Oh, sorry, excuse me. Let's talk about advantages and disadvantages. So all the advantages I talked about for user level threads are now disadvantages for kernel level threads. Okay? Because the kernel has to be aware of the threads. Every thread management function is a system call, lot more expensive. Okay? Every scheduling decision involves context switch at the kernel level, more expensive. Okay? You no longer can pick the scheduling policy for threads because you are now going to have to use the OS scheduling policy, because that's what is scheduling threads. Okay, you can't say this, I want to pick something else and so on. Okay? Now all the disadvantages now become advantages, which I will go back 2 slides. So you can now have one thread block, but the rest of the threads can execute. In user level threads, if one thread blocks, the entire process was blocked. Okay? You can take advantage of parallelism, which you couldn't threads are not going to compete within the process, they are going to compete at an OS level across all threads in the system, not just within that process. You had a question there? Okay. Is that clear? So essentially everything has actually been flipped. That's the only difference between the two. Okay. Now it should be said that most operating systems today do actually support kernel level threads. Okay. User level thread packages were kind of the way threads were implemented when they were first designed, and OS did not have explicit features and so on. But now most operating systems do, so you can actually go and examine how many threads are within your process by actually looking at the address of the processes that are executing and so on. Okay. All right. So let us now talk about, there was a question asked about how can you make the user level threads more useful from a kernel's perspective. Okay, so there is a mechanism, OS mechanism called scheduler activation, which tries to bridge the gap between user level and kernel level threads. It says user level threads have some advantages. They are efficient, they are lightweight, you can pick different policies and so on. How do we get rid of the disadvantages? How do we let the kernel know that this process actually has multiple threads in it and what each thread might be doing, because that's not visible to the OS normally. Okay. So scheduler activation is a mechanism which essentially allows the process user level threads library and the kernel to exchange information. The scheduler within the user level threads library can explicitly tell the kernel saying there are 10 processes here. If one process does IO, don't just block it, there are other things that can happen. Okay, and things like that. Okay. So you can have this collaboration between the user level threads library and the kernel scheduler in order to take user level threads and remove some of its disadvantages by explicitly passing information that the kernel wouldn't know otherwise. Okay. That's essentially what scheduler activation is. So it's an OS mechanism for user level threads. Okay. The kernel can notify the user library of kernel events that might happen, and the user library can notify the kernel about what's going on in the process, how many threads there are and so on. Okay. You still won't get true parallelism. There's no way to take a single process and schedule it on multiple cores, but you don't have to block the process if one thread starts doing IO and things like that, because you can explicitly notify the OS what may be going on. So the library can inform the kernel when threads are created, so the kernel has an accurate thread count, and you might get more CPU time if you have lots of threads, because the kernel might say there are lots of threads to execute, so we shouldn't just treat it as a single threaded process and so on. So you can provide preferential treatment based on the number of threads, which you wouldn't do otherwise. Okay. So this is a mechanism which allows this information passing to be enabled, and in doing so you can make better overall decisions in the system. Okay. Yes, your question.
Connecting that part, why can't here be true parallelism when you are having, and then the kernel knows how many threads have been spawned?
Yes. Question is, why could you not actually get true parallelism if the kernel actually knows how many threads there are? To get true parallelism, you need to actually control the registers and things like that, because the way you are going to schedule it is you are going to load the program counter of that thread into the register and then let that thread execute. If you don't see the presence of those threads, that's harder to do, okay, because then you are depending on the library and so on. So that now it is maybe possible to extend this scheme and try to do that too, okay, but the way it was designed, that was not possible. Okay. All right. So now I'll talk about this lightweight process, which was actually something that was mentioned earlier. Okay. So essentially, there's yet another abstraction that sits between the notion of a traditional process and the notion of a thread, which is called a lightweight process. Okay. And this was an abstraction that was designed in what used to be called the Solaris operating system, which I think no longer exists today, but it was a very popular Unix operating system in the 90s and even in the early 2000s. The best shown with a picture rather than the slide. So what this technique, just like scheduler activation did, also tries to get best of both worlds. Okay. You want some benefits of user level threads, you want some benefits of kernel level threads. This is yet another way to do that. Okay. And the way you are going to do this is you are going to decide for every process what are the number of schedulable entities that the kernel is aware of. Okay? If you say every thread that exists in the process has a corresponding schedulable entity within the kernel, which means there is 1:1 mapping between a thread within a process and something that the OS can schedule, you have exactly the same scenario as pure kernel level threads. Okay? Because whenever that schedulable entity runs, that thread runs. Okay? At the other extreme, if you say that entire process has one schedulable entity and all the threads within that process map onto that one schedulable entity, you are actually making it the system look like a user level threads process, because there's only one thing that you can schedule for that process and some thread within that process has to run. Okay? But you can have any mapping in between all the way. So you have on the one hand 1:1 mapping, on the other hand you have n:1 mapping. Okay? But you can say this process has 25 threads, I want 13 schedulable entities, and I'm going to have some arbitrary mapping. These 3 threads map onto this thing, these 2 threads map onto this schedulable entity, and so on, and create a more complex mapping. These schedulable entities are called lightweight processes. Okay? And you will see here, okay, this is the same picture. Now there are arbitrary number of things that the kernel can see that is mapped, that the process maps onto. In this case, you have 5 threads, okay? And there are 2 lightweight processes, and there is an arbitrary mapping of this lightweight process to those of those threads to the lightweight processes that the programmer can decide. You can say this is the more important thread, it gets its own lightweight process. These 4 threads can be mapped onto one lightweight process and share that lightweight process. Okay? Again, the scheduling decision is 2 level. Okay? First, you are going to pick a lightweight process to schedule based on all of the policies we talked about. If more than one thread is mapped onto that lightweight process, your library scheduler will run and say which of those threads should I run. Okay? So you can construct any arbitrary mapping. If you have 1:1 mapping, there is nothing to be done at the user level. Whenever you pick a lightweight process, there is exactly one thread to run. There is no decision. That's the same as kernel level thread. If you have n:1, every time you run, you have to pick between all of the n threads. Okay? Or you could have anything in between. Okay? What this allows you to do is it gives programmers a more powerful tool that decides what is the true level of parallelism the kernel should support for this process. Okay? Should there be lots of parallelism, in which case you will create lots of lightweight processes and mostly a 1:1 mapping? Or do you not want too much parallelism? Okay? Do you want just less parallelism, which means you create fewer lightweight processes and multiplex lots of threads onto that lightweight process? So you, the programmer, can decide. It's no longer, you are no longer stuck between user level process or kernel level, sort of user level threads or kernel level. This allows you to span that entire spectrum based on any mapping you choose to design. Okay? So these are called LWPs. Again, scheduling decision is 2 level, depending on the mapping of actual threads within that process to the lightweight process. And because you can do this mapping in any arbitrary way, you can still get true parallelism and all of those nice things. Okay? But you can also implement whatever library scheduler you want. That's another good thing here. Okay? You can have different processes, pick different policies. You can say this one does round robin, this one does something else. So you get some of those advantages back. Okay? So scheduler activations and lightweight processes are 2 ways by which you can take the user level threads and kernel level threads and try to get advantages of all of them in one system. Otherwise, you have to pick one or the other. Okay, so 2 independent mechanisms, but they are both trying to say we would like the best of all worlds in some sense. Okay, any questions here? Yes. Do lightweight processes share address spaces? Indeed, they do. The lightweight processes belonging to one process share that address space. And so do all the threads that are within that process also share that address space. Lightweight processes belonging to independent processes don't share address spaces because each of them have their own address space. Okay? Is there any other question? Okay, so we are going to stop here. We ran out of time. We'll continue next time.